because the periodic table is arranged the way it is, we can determine some periodic trends. So we're going to look at 4 periodic trends. The first one, atomic radius. Radius is the size of an atom. And the radius tends to increase from top to bottom and decrease from left to right. So let me give you an example periodic table here. And we'll look at the trend of atomic size or atomic radius. Increases top to bottom, decreases left to right. Another way to look at that, francium is your biggest element. Helium is your smallest element. So that's kind of the way I remember atomic size. Biggest francium, smallest helium. When you're looking at atomic size, let me do a comparison. Let's say calcium compared to chlorine. You'll notice they're in different rows, but they're also in different vertical columns. Top to bottom makes a bigger difference when you're comparing atomic size. So since calcium is in row 4 and chlorine's in row 3, calcium is a lot bigger. You always look top to bottom before you look left to right with atomic size. So calcium's a lot bigger than chlorine. So why does size increase down a group? I'm going to go back to electron configurations, and I will compare lithium to sodium. Now, sodium is bigger because it's further down in the group. But if you look at their electron configurations, they would look something like this. Lithium ends in energy level 2. Sodium ends in energy level 3. Well, since sodium has more occupied orbitals, energy level 3 as opposed to energy level 2, that by default is going to make sodium bigger. If you're in energy level 3, you're further from the nucleus. Energy level 2 is closer to the nucleus. But another reason they get bigger as you go down a group has to do with the shielding effect. Electrons, and we'll look at lithium, electrons repel each other. Well, lithium has 1s electrons that are repelling the 2s electrons. So there's some shielding there. There's some repulsions. The protons in the nucleus tend to pull the electrons close. But since these 1s electrons are closer to the nucleus, they shield the 2s from the nucleus. So that's what shielding means. The electrons repel each other. However, look at sodium. Sodium's outer shell electron is the 3s. It's being repelled from the nucleus by all of these electrons, 1s, 2s, and 2p. So there's more shielding here. There's more repulsions. And since there's more repulsions, that makes sodium a lot bigger because those electrons are repelling each other and kind of pushing it outward. As you go across the periodic table, size decreases. Again, I'm going to go back to electron configurations, and we'll look at nitrogen and oxygen. Electron configurations for both end in 2p, but nitrogen is 2p3. Oxygen is 2p4. Now, the shielding effect is constant. If we look at the shielding effect, the 2p electrons are shielded from the nucleus by the 1s and the 2s. So the shielding effect is constant. However, the number of protons has changed. Nitrogen has 7 protons. Oxygen has 8. And protons tend to pull electrons closer. Since the shielding effect is constant and oxygen has more electrons, oxygen is going to be smaller because those protons pull the electrons in closer to the nucleus. Second trend deals with ions, and there are 2 types of ions. There are cations, have a positive charge. These tend to be your metals. And anions have a negative charge. These tend to be non-metals. So the second trend deals with ionic size. Cations, positive ions, are always smaller. And I'm going to compare calcium to its ion. Calcium forms a positive 2 charge. Now, both of these have 20 protons because they are calcium. The difference is the number of electrons. The atom has 20 electrons, whereas the ion, since it's got a positive 2 charge, only has 18 electrons. Same number of protons are pulling on less electrons. That's going to make the ion much smaller. Protons attract electrons. Well, there's less electrons to attract. Going to pull those electrons in closer, and calcium plus 2 is a lot smaller than the atom. Anions are exactly opposite. I'll look at chlorine. Chlorine forms a negative 1 charge. Now both of these have 17 protons because they're chlorine. The difference is the number of electrons. The atom has 17, but the ion has 18 because it's a negative charge. It's got 1 more electron. Same number of positive pull in the nucleus, but there's more negative out here. And so that means those protons cannot pull those electrons in as close, and the anion, Cl-, is going to be a lot larger than the atom. And that's always the case with ionic size, which is our second trend. Third trend is ionization energy. This is defined as the energy required to remove an electron. And we're looking at just the first ionization energy, which is the energy required to remove the first electron. The trend for ionization energy, it tends to decrease top to bottom, increase left to right. Exactly opposite of atomic size. Let's look at a periodic table. And again, the way that I remember these for ionization energy, largest ionization energy is helium. It's going to take a large amount of energy to remove an electron from helium. Largest amount of energy. Smallest ionization energy, down here. It will not take that much energy to remove an electron from francium. Again, just like with atomic radius, atomic size, if I'm comparing two elements that are in different columns and in different rows, top to bottom makes a larger difference than left to right. So if I'm comparing calcium to chlorine, and I want to say which one has the largest, since calcium's in row 4 and chlorine's in row 3, based on ionization energy, Cl has a lot larger ionization energy than calcium. So top to bottom makes a larger difference than left to right. Group trends in ionization energy. As the size of the atom increases, we have more electrons that repel the outer electrons from the positive pull, and thus it's easier to lose an electron for an element near the bottom. Again, if I go back to lithium and sodium and I go back to their electron configurations, I think this makes it just a little bit easier to visualize, but electron configurations again look like this. There's more shielding with sodium because there's more electrons here in the closer to the nucleus, more inner shell electrons. So there's more shielding down here, which means the outer shell electron is not held on as tightly, and so it's going to be easier to take this electron away because there's more shielding with sodium than compared with lithium. So lithium has a higher ionization energy than sodium. It's going to take more energy to remove lithiums because lithium has less of this shielding. There's not as many repulsions going on with lithium as compared to sodium. Periodic trends across a row. The positive charge increases across a period. And again, we could go back to my examples before, nitrogen and oxygen, and go back to their electron configurations. Positive charge increases across a period. Nitrogen has 7 protons, oxygen has 8 protons. So that means there's an increase in the attraction of the nucleus for an electron. So it's going to be harder to remove an electron near the right of the periodic table. It's going to be harder to remove oxygen's electron than nitrogen. So oxygen has a greater ionization energy than nitrogen. It's going to take more energy to take away an electron from oxygen because of that additional proton. Third trend, ionization energy. Fourth trend, electronegativity. This is the ability of an atom to attract electrons when the atom is in a compound. Now we're going to do some of this a little bit later. We're going to use what are called Lewis dot structures. But electronegativity is this. So there's a bond between hydrogen and fluorine. Another way to write this would be this. There's a bond right here. Well, here's the bond. That's the electrons that are forming the bond. Electronegativity is basically a measure of which atom, in this case hydrogen or fluorine, wants these electrons more. Which one wants the electrons more? The electrons are not shared equally in most cases. One atom usually hogs the electrons. Well, the trend is decreases top to bottom, increases left to right. Fluorine has the strongest tendency to attract electrons. So fluorine has the highest electronegativity value. Noble gases, the ones in group 8A, are omitted because they don't form many compounds. So let's go to the periodic table again. Electronegativity. The highest value for electronegativity is F. And then it kind of decreases as you go this way on the periodic table. Now, with the other trends, top to bottom made a bigger difference. However, when we're looking at electronegativity, we're looking at the distance from F solely, the distance from F. So, for example, if I'm comparing sodium to sulfur to bromine, kind of find these in the periodic table, they're the same distance from F. You have to go through one element to get to F. And so these would have relatively the same value for electronegativity. So with electronegativity, do not look top to bottom first. Look solely at the distance from fluorine to determine which one has the highest value for electronegativity.